Welcome to section 3. In this section, we are going to talk about the electric field. In this lecture, we'll start with talking about what an electric field is and just some nature behind the electric field. So the electric force that we talked about in the previous section, it is a long-range force or a field. It does not require contact between charged objects to have the force. So it's not like normal force or tension force. You need to push or touch an object or attach an object with a string. There are forces that require direct contact. But electric force is more like gravity force. If you drop an object in air, the object will just fall downward because of the gravity force. There does not require some direct contact to the object. So if you have heard of gravitational field, the electric field is similar to the gravitational field. This concept was originally developed by Faraday. It was inspired by observing the pattern when we put two magnets inside irons. Then we will observe the pattern as shown. As we'll learn later in the course, this pattern is the electric field. Let's look at the concept through the Newtonian model. So when we have a source charge, such as A, if we put a test charge around the source charge, let's name the test charge charge B. Then A exerts a force on B. So there's a force pointing from B to A, and we call that force of A on B. That is when we look at the concept in the Newtonian model. However, in the field model, suppose we have a source charge A. Then this source charge would alter the space around them by creating an electric field E. And when we insert the test charge B, then this test charge will experience a force exerted by the field. So it will be force of field on B. And note that this field was created by the source charge. So the test charge does not require to exist in order to have the field. Remember, I just said that the electric field is similar to the gravitational field. Similarly with gravity, suppose there's the Earth, and it creates the gravitational field around it. We do not need an object in order to have this gravitational field. But when we do have a test object, suppose I put a rock here, and when I release it, the rock will feel the gravity force due to the gravitational field. But the field is always there whether I put the rock here or not. Similarly with electric field, the field was created by the source charge. So whether I put a test charge inside the field or not, the field is there. And we found that the test charge Q prime experiences different forces when we place it at a different location in the field. So then we define the electric field at the location as force on the test charge divided by the test charge. So the unit for electric field would be newtons divided by coulombs. The electric field is also a vector, and we call the magnitude of E as the electric field strength. Here's a quick quiz. A test charge of 5 microcoulomb is at point P, where an external electric field is directed to the right with a magnitude of 5 times 10 to the power of 6 newtons per coulomb. If the test charge is replaced with a new test charge of negative 5 microcoulomb, what happens to the external electric field at P? A. It is unaffected. B. It reverses direction. C. It changes in a way that cannot be determined. The answer is A. It is unaffected. Because, remember, electric field is not dependent on the test charge. It is dependent on the source charge only. So in this problem, we only change the test charge. So the electric field at P would be the same. We often want to determine the force on the charge Q prime exerted by a known electric field. So using the definition we just had for the electric field, we can solve for the force acting on the test charge, which would be Q prime, the test charge, times the electric field. So from here, we noted a few points. Direction of the force depends on the sign of test charge. If the test charge is positive, then the force would be in the same direction as the electric field. If the test charge is negative, then the force on the test charge would be in opposite direction than the electric field. And I think of the electric field as a generalization of force. Electric field tells us everything about the source charges and nothing about the test charge. Here's another quick quiz. A free electron and a free proton are released in identical electric fields. How do the magnitude of the force exerted on each particle compare? A. It is thousands of times greater for the electron. B. It is thousands of times smaller for the electron. C. They are equal. D. It is 0 for the electron. And E. It is 0 for the proton. The answer is C. They are equal. Here we are talking about the magnitude, so they are equal. Because a proton and an electron, their magnitude of charge is E. For proton is positive E, for an electron it is negative E. And the force acting on the test charge in an electric field is the test charge times E, the electric field. So since they are placed in an identical electric field, and they also have the same magnitude of charge, so the magnitude of force exerted on them are identical. Here's another quick quiz. An object with negative charge is placed in a region where the electric field is directed vertically upward. What is the direction of the electric force exerted on the charge? A. It is upward. B. It is downward. C. There is no force. D. The force could be in any direction. The answer is B. It is downward. Because the electric field is upward and the test charge is negative, and we learned that the force is the test charge times the electric field. So the force and the electric field will be in opposite direction when the test charge is negative. And that is the end of the lecture. In the next lecture, let's look at the electric field from a point charge.